Okay, so welcome to GeoOnsdag today. Obviously, I'm not Bernd Oelzermüller, but I'm Stefanie Werner, and I'm professor at the Geoscience department working at the same Center for Planetary Habitability as Agata. And it is my pleasure to introduce her. But before, I would like to say briefly what the GeoOnsdag is all about, and that is to introduce research at the department in a semi-popular way, to introduce research done here and also to attract a lot of students, and also colleagues shall be informed what we are doing. So with this, Agata Krzesinska has started working at University of Oslo in 2018, where she started working on a project called Planetary Terrestrial Analogues Library. Her actual background is and research topics are related to meteorites. In this case, I shall emphasize not only Martians, even though today it will be a lot about Mars, and terrestrial analogues for Mars. She is also participating in ESA ExoMars rover science support team, and recently she was very active, or is still very active, as a member of the NASA-ESA Committee for Mars Sample Return, Sample Receiving Project Measurement Definition Team, and that means she can decide what they will do with the samples when they come to Earth. She further is also the manager of the Mars Sample Return Analog Sample Library at the Natural History Museum, and she is member of the steering committee for Norwegian Meteor Network and classified 3 most recent Norwegian meteorites which have been falling, one in Oslo, Vale and Jordan, and equivalent are the names of the meteorites. And now I stop talking and give Agata the word on bringing rocks from Mars to Earth.
Thank you for introduction and thank you for coming. And yes, I will be talking about rocks from Mars to Earth, and will try to tell you mostly why is it important, less within my speciality, how is it going to be, but also the thing which is not immediately obvious, are we ready to work with them or not yet? So to start, many of you might remember February 2021, in the middle of pandemic, out of sudden there was a bit of noise in the media that the rover landed on Mars, and there was the streaming of the descent and landing of the rover, and there was a lot of memes about search for life and the pandemic context, and a lot of people were asking, but why? Why is it so important? Is it the first rover which will land on Mars? And of course, it's not the first rover, and it's a very fair question, because actually landing rovers on Mars has tradition of almost 50 years. And why then this one was special? After, here are shown 4, but there was actually 9 successful landing attempts through various agencies of the world. And why Perseverance was so special among of those? Mostly because it has this drilling, can you see my cursor? No, you can't. But it has this drilling device which can drill into the subsurface, seal the samples, and the idea is that this is the first step of Mars sample return. And this is something entirely new in the science of studying Mars. We don't have so far samples from Mars. But you may ask, why do we want to have samples from Mars? And since we are studying Mars remotely, isn't it enough? Do we really need to have all this effort to bring them to Earth? And mostly my talk is to answer these questions. So first of all, why Mars? Because Mars has some geology, and it was seen already in 17th century through telescopic images that unlike other planets in the solar system, so Mercury, Venus, on Mars there are some terrains which mean that there is something going on. And even if on that time people weren't able to say what exactly is the process behind that, there were some supposition about that there are some polar caps, that there are some terrains of volcanic activity, for example. There are clouds, meaning that there is an atmosphere. And altogether, it means that Mars may be quite similar to the Earth, meaning giving us another point to study geology. And here I want to emphasize something which might be important with later findings, that Mars is more or less half a diameter of the Earth. So it's quite small planet. So we wouldn't expect that active geology, yet it exists. And when the proper planetary science or exploration started, Mars was one of the planets which was visited by orbiters, landers, and so on. And they very clearly showed that this planet is very active igneously. For example, here in the images, you can see the massive lava plains, meaning that there was some eruptive volcanoes on Mars. And on the map on the left, you can see the areas which are known as the volcanic provinces with a lot of lava plains. Also, since the early exploration of Mars, it was known that it has massive volcanoes. The three on the top image as volcanoes in Tarsis, seen already in late 70s. Below is Olympus Mons, which is the highest volcanic mountain in the solar system. Comparing to our mountains, Olympus Mons, 21 kilometers height, Mount Everest, almost 9,000 meters, and even the Mauna Kea, the highest mountain of Hawaii, calculated from the bottom of the sea, is nothing compared to the height of Olympus Mons. So this is especially impressive when you take into account that Mars is much smaller than the Earth. And additionally, Mars has tectonic features. Here in the image, we can see so-called Valles Marineris, which is massive canyon. Comparing to Grand Canyon, Colorado, you can see at the graph here, it's almost not noticeable, the size of Grand Canyon. And if we put the Valles Marineris within this context, it would actually cover whole US. So again, on the quite small planet, we have features which are very impressive in size. And looking at the map here, you can see that Valles Marineris is located in a way correlated to Tarsis, so the volcanic province, meaning that these features formed in a way through common process or were interacting with each other, which is very interesting to understand how the planet evolves and how the interior interacts with the surface. And additionally, Mars had some water in the past. We know that it was in the past because when you look at the topography, you can notice the reddish areas, which are higher, have a lot of craters, the southern part of the Mars, while at north, the bluish on the map here, they are smoother, meaning that there was less impacts accumulated over time, meaning that they are younger. And when we look at the distribution of the minerals, which in terrestrial conditions on the Earth required water to form, we can see that these southern highlands are associated with a lot of signatures of water, meaning that in the past, Mars had flowing water. And indeed, there are morphologic features like river deltas or networks of valleys from the rivers or from the water flowing on the surface. So all that implies that Mars, at least in the earliest epochs, was a very dynamic world, quite similar to what we are looking at Earth to study geology. And the most fascinating part of that is that when you look at the timing from the accumulation of the craters, we can figure out that this water and volcanoes and impacts on Mars were active more or less in between 4 billion years ago to 3.6. The border where it stopped is not entirely clear, but that would be the rough timing. While if we compare that to the Earth timeline, we can see that it's exactly the time from which we don't have record on the Earth. In our timeline, we are used to see it stretched with the last 500 million years, because that's the time for which we have a big geological record and a lot of details. But in reality, we know a lot only about these last 500,000 years. For the time from, let's say, 2.5 billion years ago to 500 million years ago. We know that everything was starting to operate, but how, what, that's very vague. And we have only remnants of the old crust or of the old worlds. While on Mars, this is the time when everything was happening. And when you look at this surface here, the red areas are those which stayed as they were formed in the Noachian, meaning half of Martian surface is of the age which is totally removed from the surface of the Earth. So as some people are saying, Mars can be Rosetta Stone to understand what was the early Earth like, including the times when the probably life formed. So that's basically why Mars is interesting and why it's so much investment into studying of Mars. But the other side of that is that studying remotely has a lot of limitations, right? And for example, one of the techniques which can be used is the spectroscopy with the near-infrared or with thermal or whatever technology is able to provide. And looking at the infrared data, you can figure out some signatures which are typical for some minerals which we know from the Earth. And for example, in this graph, we can see that there are signatures in certain places of Mars which suggest that there are present clay minerals. So like the phyllosilicates, these water-binding minerals, and they contain iron and magnesium with different proportions, and also we can figure out what is the oxidation state of iron, meaning if it's iron 2+, iron 3+. And in a typical geological work, it gives a lot of insight into was the environment oxidative and so on and so on. And work done to, let's say, map the distribution of various clay minerals with different iron content and different oxidation stage shows that there is some variety. On this map with the different colors, basically, you can see that there are some changes in that. And natural thinking would be, okay, there are some processes which segregate iron from magnesium, but to address that, first you have to know what is the content of iron in the bedrock, in the primary rock, before it was altered. And to get this information, you have to work with another data set from gamma rays, which can give information about the content of certain elements in the rocks. But there is one caveat, that the resolution of gamma ray spectrometers is 300 kilometers per 1 pixel, while for near infrared is something like 50 centimeters. So comparison is already not easy. And to let you understand how difficult it might be, that's the map of the area which we know, right? We know that there is a lot of variety and various rocks. And here I made 300 kilometers per pixel. So I don't know if Oslo Reef is at all visible here, and if you could have any idea of the bedrock composition, right? It's just a blurred. We can see that there is some variety, but it's not easy to know what is behind that, right? So working with these data sets is extremely challenging. But then we have landers and rovers, right? We can send them to Mars with some payload, with some instruments, and we did it as a community 9 times, but we cannot send rovers everywhere. And example from one of the missions. There is the map of Mars. And first requirement is that it's hard to land with anything on Mars at the altitude higher than -2 kilometers. So on this map, you can see the scale bar, and -2 kilometers is something in the green area, right? So anything which is red or greenish is too high, and the parachute will not open to slow down the stuff to not crash on the surface, right? We can land only lower than -2 kilometers. So all the gray stuff is out. You can see that volcanic provinces, no way to land there, right? And also the southern hemisphere, which, as you remember, may be the most interesting. It's not easy to land there. Then another requirement is that we have to have some power, so somehow around equator. So again, narrowing down. And for example, if you really want to land on the Noachian terrain, the only patches are the green ones where you can put your rover on lander. So choice of the place is really challenging. There is a lot of limitations, yet still the rovers provide a lot of useful data. Another problem is that when you send something by rover, it has to have simplified payload, it has to work on unprepared samples, it has to have quite rough technology, right? And even if engineers are very creative and innovative, it's not easy to give information, for example, on geochemistry, geochronology, trace elements, or microstructure. That is all out of our reach. And for example, here is the Curiosity rover, so one of the most advanced payloads. And the list on the right gives the techniques which were deployed with the payload. So there was some fluorescence imaging, or laser-induced breakdown spectroscopy, shooting on the rocks, giving approximate composition. There was XRD, working, of course, on the exposures, on the outcrops, not on the powders. So we've got some estimated analysis from this place, but of course, nothing very detailed. And the last limitation, of course, rovers cannot go very far. Typically, the nominal time of mission is 2, 3, maybe 4 years. The champion in this was Opportunity, which was active for 12 years, even if it was designed to, for sure, work for, I can't remember, 5 years maybe, but it was extended, and it was doing so well that it managed for 12 years. And within this time, it traveled only 45 kilometers. So again, imagine that you land rover in Norway, and you happen in land in Drammen, and you cross more or less to the center of Oslo. What image of the area would you get from that, right? And you travel with the payload, which is basically cameras and rough analysis. So it shouldn't come as a surprise that the image which we get from rovers sometimes is quite different from what we would expect from the orbit. And here is an example from Gale crater, one of the locations, which analysis by rover showed that there are rocks like trachytes, trachyandesites, so kind of alkaline series, which was highly contradicting the image from the orbit, here marked as TESS, which was saying that Mars is basically either basalt or basaltic andesite. And it's great that there is a larger variety of rocks on Mars, but the question is this place something special which we just did not know landing on? Or maybe Mars in a local scale is much more complex than we perceive it, right? And then, of course, all the questions which come up. Why, what processes, which we cannot get with the analysis with payload which we have. That's the image, by the way, on Gale crater. So, yeah. And a bit more, maybe, detailed image of Mars can be given from meteorites from Mars. There are 300 rocks or so that we know that they come from Mars. And I will, before you wonder how we know, I will answer that. So that was a long historical debate to prove that these rocks come from Mars. First hint was given from the fact that they are basalts, meaning that they required larger body and quite active geology, which is not possible for the asteroids, which are typical source of the meteorites. And the crystallization of age measured on these rocks was something like 100 to 600 million years, meaning that the planet had to be active for quite long. And the only suspect was really that it has to be Mars, because no other bodies in the solar system can maintain it. Then, with time, when more and more of these meteorites were appearing, people noticed that they all cluster in mass-dependent fractionation line for oxygen isotopes, meaning that it's something different than for chondritic meteorites, which are very primitive matter, not following the mass fractionation rule. And they were all clustering in one area, different than the Earth and the Moon, but still something planetary. So there was a hint that they are from Mars. And the final evidence for that came when rover or lander was landing on Mars and measured during the descent composition of atmosphere. And then the data on certain elements, on noble gases, from the atmosphere measured by the lander matched perfectly the air bubbles which were captured. You can see in the image here, the black spots are shock pockets from meteorite, which formed when the meteorite was launched from Mars under high pressure. And then, within this melt, it captured a bit of atmosphere. And the composition of the atmosphere captured in these shock melt pockets matches what Vikings measured on Mars. So that's our only proof that the meteorites are from Mars, but it's enough to proceed. And they are very fascinating rocks. They are mostly basalts. From the texture, you can see that they are both intrusive rocks and also lava, pieces of lava which was flowing on the surface of Mars. For the more geological insight, they are sometimes cumulates. Sometimes they have a more evolved composition with quartz and feldspar, so something like rhyolitic composition, meaning that all the processes which we know from Earth, the complex emplacement, crystal fractionation, accumulation, contamination, and everything which happens during the magma ascent on the Earth happens also on Mars. So Mars is not that simple. It has its own geology and is similar to the Earth, but a bit different with the compositions, right? But problem with meteorites is that the ages are quite young. And if you remember the introduction part, this would be in the most boring time of Martian history, this 600 million years to 100 million years, right, in Amazonian, while we are mostly interested in the earliest, in Noachian. So first, it's quite curious why with the planet dominated by old material, we have rocks mostly ejected from the young terrains, but that's another story. But it's also a pity that with these rocks, we don't have access to what is the most interesting. And actually, there are two meteorites of the truly Noachian time. One is orthopyroxenite, and the other one is the regolith breccia, which is shown here. Regolith meaning that everything which was created by impacts and all the processes and then lithified, and somehow it managed to get arrived to the Earth. And within this breccia, you have small clasts. On the images here, you can see that they are below 1 millimeter in size, clasts which have more alkali-rich composition like monzonite. And that immediately suggests a question, was there some difference in between volcanism on early Mars and on the recent one? And if so, why and how, right? Also, Martian meteorites give us insight to the interior. They are igneous rocks, so studying them in laboratories, we can get something more about the planet itself, not only about the rock, right? And if you look at the graph here, which is maybe a bit complicated, but it doesn't matter, these are the isotopic signatures of the sources which are used in the geochemistry on the Earth. And there are sources which are depleted, enriched in certain elements, and from that you can figure out whether the rocks come from the mantle, from the crust, or was contaminated on the way, and so on. And as you can see on this graph, meteorites come from several different sources, right? And they differ quite highly in the signatures, meaning that the Martian mantle, the interior, has to be quite heterogeneous, which is, again, quite surprising for the small planet to be that heterogeneous. Also, planet which has no evidence of the plate tectonic, which is causing, or at least it's assumed on the Earth to cause the heterogeneity of the mantle, right? But also, what is interesting here is that, for example, in this orange field of enriched shergottites, they have exactly the same signature as one of the Noachian meteorites. And is it coincidence, or it's something behind that? Also, within the depleted shergottites, you can have members with exactly the same signature, but in the crystallization age spanning something like 1 billion years. Does it mean that there was a volcanic activity continuously going on for 1 billion years? That's a question which would require some context, right? And in this sense, what does this individual site or the same source mean? When you go to the fieldwork on the Earth, you choose a localization, you go to the outcrop, you do the investigation, sampling, and then proceed with the details, right? Wait, what? This way. We increase level of precision of analysis, but it all makes sense only to put everything back to the location on the map and eventually to decide something on the geodynamic setting, right? And actually the most precise analyses are only needed to say something about the interior, right? And if you happen to have something strange in the field or something which kind of doesn't follow the known paradigms, it's even better because you can forward the science, right? And imagine now that you have two rocks without knowing what is the context. You have, for example, piece of rhyolite and piece of basalt. Do they come from the same place? Or is just a coincidence that they have similar signature, or right? It's kind of puzzle and a detectivistic work which you cannot resolve. So, trying to summarize that, it's as on the flow with the Earth, meteorites, you can always have a precise analysis, but it will never give the context. And simultaneously, we have some analysis on Mars, which give us the counterpart of the fieldwork, but we never get the precision which would be needed to understand what is the interior, right? So we have everything, but just disconnected. And that's why we need Mars sample return, to do the field observation on the Mars, and then all the analytical work on the samples with the context. And the key part here is to collect the samples, send them back to Earth, and study, right? And that's how. So first step is already done. Perseverance sampled samples, it's still going on, but set of the catch samples, 10 samples, were already deposited in one place. It's called Three Fork Depot, which was done after 2 campaigns. So the igneous floor of the crater plus the delta fan are sampled and stored in one place. That's how they look on Mars. And at the same time, Perseverance is continuing its work and sampling. And if something happens to the rover that we would lost connection or something like that, we can always go to this location for the samples. But if the Perseverance performs well, maybe the samples which are still on the rover will be the target for return. But for that, we are ready. But Perseverance will not get back to the Earth, right? Perseverance will finish mission on Mars. Second step will be to send another mission to Mars, which will deploy so-called fetch rover, which will find the tubes, the samples on the surface of Mars, launch them to the orbit of Mars, and here another complication, because if something was on Mars, it cannot enter the Earth. So on the orbit of Mars, there will be a rendezvous of another orbiter, which will shoot the samples, or the sample capsule. That will be captured by the other spacecraft, and only this return spacecraft will enter to the Earth. And it might seem the end, but it's not. And apparently we are able to do that. It takes time, it takes money, but apparently technology is able to perform these tasks. But there it's only the beginning, because the samples themselves are also biohazard. They also cannot enter the Earth without sterilization. So when the capsule will land on the Earth, it will be covered with the back case, sterilized around, put into a safe vault, investigated up to a moment of when it's deemed to be saved and sterilized. And here is the problem, because some methods of sterilization may be dangerous to some scientific questions, right? And it's a lot of wondering behind that, because each sample, that we are from the place almost Noachian in age. So each sample has a long history of igneous processes, sedimentation, impact. Also, we are looking for ancient life traces, so we want to study all this. Some stuff has to be done before the sterilization, but of course it's impossible to do everything before the sterilization within the biosafe environment. So it is important to figure out what we are going to do, right? And each sample is something like 5.5 centimeters long and 1 centimeter diameter. I brought this vial. It's kind of the size of the samples which we will bring. We will have 10 or 15 samples like that to answer all these questions, right? So we have to we have to know what we are going to do, right? So the question, I guess, is not necessary to answer. We are not ready, but we have a decade to go, and we have time to understand what is going to be done and to basically test everything. So what is going to be done, it's already approached very seriously by space agencies. And last year, I was involved also in works of this committee, which was appointing 20 scientists to figure out what exactly questions from various disciplines we will want to answer on these samples. And when we have the list, to understand what will be impact of the measurement on the sample and how it can impact other questions, to put a sequence of the investigations in a proper row and decide what has to be done before sterilization, what has to be done after. If you are interested in that, the full report of this committee will be available soon. But another part is that then, when we kind of know what has to be done, there are, of course, also areas which we don't know. For example, I think I skipped that, or maybe it's here. That some techniques, like, for example, very popular now, X-ray tomography, we don't know what impact they have on the sample. If you scan a sample with energy of 200 kilovolts, maybe it is damaging, for example, to electronic structure and then damages the magnetic record, which is one of the questions, right? So certain things have to be just tested on the appropriate material. And for that, we need analogs, meaning the rocks from the Earth, which are similar in some sense to what we expect from Mars, to run all the tests and to see what kind of impact measurements have to the rocks. Since rover is studying samples on Mars, we know something about the rocks which hopefully will be returned to the Earth. So we can collect something which we consider similar and then run the tests needed. And such collection already started to be created. It's hosted at NHM at UIO, so we are managing that. So far, there were 5 analog sites worldwide selected and sampled. From each, we have 300 kilometers, and we hope that this collection will serve the purposes of testing of the all open issues for the Mars sample return. So we are not ready, but at least we started to get ready for the return. And that would be it. My take-home message would be that actually, Mars sample return needs everyone's expertise because it's a very complex project. But at the same time, you might need samples returned from Mars because they add another dimension to the problems which probably you deal with, because Mars has geology, but it somehow goes differently than the terrestrial one. So that would be my take-home message. And if you are interested, there is a link to the project webpage. And also, if there are students who are interested in getting on board of that, we have a master project on offer. And with that, thank you very much for your attention.
Okay, thank you very much, Agata. And if you have questions, please raise your hand. And someone with a microphone will come because the streaming shall record your voice as well.
Yeah, that was a brilliant talk. Oh, okay. I thought that was a brilliant talk and great summary, and I learned a lot. These are all surface samples, and can you comment a little bit, and I know they're chosen from outflows and things, what's the progress on subsurface drilling, or is that something you think is going to change anything?
subsurface drilling meaning by Perseverance or by other missions? Yeah, so there is a plan of ESA mission, ExoMars, which is equipped with the drill which is 1 meter or 2 meters deep. So that will be the best insight into the subsurface. But this mission was very unfortunate. It was meant to be launched in 2022. Was it 22? Yes, July 2022, but in collaboration with Russia, and the invasion on the Ukraine closed the collaboration and did not launch. So it's postponed now until 2028 because there is no good window to launch yet. So it's still, to get results from this rover, it's still, again, a decade. But hopefully it will happen.
I have a question here. I was wondering which 5 areas were good analogs for Mars. You mentioned that right now.
Where are the 5 sites which are? Yes. So one is Iceland, not surprising. Other one is Ram in Scotland. So maybe I get back here. The Sita, the olivine cumulate, from the texture you can see that there are olivine grains enclosed in poikilotically enclosed in pyroxene, and it's featured quite typical for terrestrial very large dunites or the basically olivine cumulates, and the most known location for that is Ram in Scotland, so this was sampled. I have to say here that the typical problem with analogs is always that terrestrial mafic minerals are much more rich in magnesium than Martian ones. So there is never perfect analog, but this one is close enough. For Mars, the sample was found in Hart Mountain in Columbia River basalt. So again, the igneous province and first stage of the emplacement, and there are rocks which were texturally similar to Mars. Of course, there is again a lot of mismatches, but they were identified. And Iceland is the third one, and there are 2 for the sedimentary rocks for the delta, sandstones which are cemented with carbonates and sulfides. So they are Salton Sea and rich basin in US.
Hi, Agata, thanks. Just asking from astrobiological perspective, is there any information on rocks which have some form of carbon in them?
You mean for analogs or for Perseverance?
From Perseverance.
Yeah. There are laboratories measuring the organic molecules. There is Raman spectrometer on board, and there is whole team working to figure out the presence of organics and, yes, to approach the question of was there any life form. Did I answer?
More if there is any news of it?
There is any what?
Any news that you found something there?
So any evidence for that? No, nothing, at least nothing announced, yes.
Maybe a stupid question, but why is the planet red?
Well, it's not anymore. It was in the past. So, what? Red. Because it has oxidative conditions on the surface, and it contains the rocks contain a lot of iron, meaning that like we have when you have a bit of steel or anything containing iron exposed to the atmosphere, it's getting rusty, and it's the same process.
I was wondering if you have to send a spacecraft to pick up the samples, wouldn't it be possible to do analysis already on the spacecraft before it returns to Earth? So you don't have to do
on the orbit, on the surface of Mars, on the orbit.
Yeah, in the orbit, because I guess they have to build the spacecraft to send it there, and then you can maybe avoid all these contamination procedures that alter the samples.
I don't think it would make life easier, because the biggest problem with getting precision of analysis is to have access to a calibrated laboratory with a good sample prep. And if we cannot have it on Mars, I don't think in the space or on the orbit it would change that much, right? It's still building huge infrastructure which we have on the Earth and do not necessarily need to invest there.
Any further questions? Yeah.
So the MMX mission going to Phobos, do you know if there's a effort to analyze them for Mars samples from their sample return?
I don't know. I'm not that following MMX. Well, in general, exploration of Phobos is considered, so Phobos is the moon of Mars, and exploration of Phobos is considered to be one technological step to prepare us for return from Mars, right? So if we are able to get samples back from Phobos, then we are closer to understand the technology of getting samples from Mars. I know that it's not answering your question, but it was just to give the background to others. But I don't know.
Yeah, I was just curious if there was a close coordination between the Mars sample return community and the Phobos sample return.
Probably there are, and for sure, I would assume that engineering and technology for sure, communication, but scientifically, nothing that I'm aware of or anything which I could comment on.
Okay, thanks.
Yeah.
It's usually the same people who study the composition. So, any further question? If not, I have one. How many more samples, analog samples, will be maybe picked for the library?
It depends, because Perseverance is still going, and the 5 sites are for the 2 campaigns, the igneous crater floor and then delta front. Perseverance already went through delta, approached the margin of the crater, and is going to explore beyond. So whatever we meet there, we might need analogs, and for sure the rocks there will be different from what we encountered so far. So depends on money, interest, availability, and yeah. And also for these sites, it's not that one analog answers everything. There might be better analogs, there might be analogs which are better to answer specific questions, right? Because for someone who is interested in texture, maybe that's a good analog, but for someone who wants to look, I don't know, at the grain size, it might not be entirely the same good analog. So everything may need to expand depending on what needs to be done.
Okay, if I don't see any more hands, I thank you, first of all, Agata, for the presentation and answers, and you to listen and ask the questions.
Thank you.